effort from the get-go.
Okay. Thanks, Sean-Joy. So it's great to be here. So I'm going to be talking about some algorithms for learning hidden variable models or latent variable models using linear algebraic methods or multilinear algebraic methods. Okay, so that's the subject matter. Just from the get-go, I should say that that we're looking at a particular concept of learning, which is that of parameter estimation. It may be familiar for people in statistics, and the main technique we're going to be using is the method of moments. Okay, so let me give you some examples of latent variable models just to motivate these ideas. Okay, so suppose you have a collection of documents, and it's a very large collection, but you don't have time to go through them all, but you just want to get a sense as to what these collections of documents are about. Okay, and your main observation, perhaps, is that these documents they're about certain topics, and you can kind of tell what the topics are based on the words that appear in documents about those topics. Okay, and documents might express one or more of these kinds of topics. So here's an article from the New York Times, just the headline part of it. Seems to be something about sports, it's maybe something about business or finance. And so, you have a lot of these New York Times articles, and you don't have time to read them all. You just like to know what are the different topics that this collection expresses, and maybe how prevalent are these various topics. And so one thing you could do is to then fit a particular latent variable model to this collection of data. And for this task, you would probably use something called a topic model. There are various kinds of topic models. One of them that you may have heard of is latent Dirichlet allocation. Okay, so these are, the ones I'm going to describe are much, much simpler than perhaps some of the models that Mike Jordan talked about on Wednesday. Mike and Ham wrote. So these are parametric models. So in this kind of model, there are k different topics, and topics express different distributions over words that are likely to appear in documents about those topics. And we're going to identify each document with a particular mixture of different topics. So maybe one of those, the previous document that you saw was somewhat about sports and somewhat about business. And the words that actually appear in the document will make this assumption that they are drawn IID from a particular mixture of the various topic-specific distributions on words. Okay? So perhaps in the previous document, it was 70% of the words will be about sports, 30% will be about business or finance, and the words that you see in the document are assumed to be drawn from this particular mixture of those two distributions. Okay, so that's the generative model. That's the statistical model, the story about how data appears from distributions from these models. And the learning problem then is that you have this collection of documents. You want to get an idea about the specific distribution from this model that generated the data. Okay. And so you're given a collection of documents, perhaps some of the hyperparameters. We're going to just assume these things are known, like the number of topics and so on. And given this data and these hyperparameters, you would like to estimate the model parameters. Okay, so in this case, perhaps you want to estimate the various distributions on words for each of the topics, and also the weight of each of the topic. How prevalent are these different topics in the corpus? Okay, so that's the topic model. Now you might think that actually this might be a fairly simple task to estimate these various things. These are just counts of how often do various words appear from documents about a topic, and how prevalent are these topics. This just sounds like a task for just counting or something like that. And indeed, it would be the case if somehow someone had gone through all of your data and all of the words in the documents and annotated every word with the identity of the topic, the source topic for that word. Okay, so you go through all the documents and you say, okay, these words, they're all about the sports topic, so I'll just write down one for each of these words. And then these are sort of probably generated by the business type of topic. I'll write down a 4 for all of these things. And you do this for all of the words in your documents. Okay. Now, once you have such annotations for all of the words and all of your data, it actually is very easy to estimate the parameters of the model. Right? You just do some counting You divide by various numbers, and then you have, you have some reasonable estimates of all of these parameters. So in this sense, once you have these kinds of annotations, estimation can, in some sense, be done directly. Okay, but of course, this requires you to do all this kind of annotation, and the whole point of using this model was that we didn't want to read all of the documents and spend all this effort. We usually do not have such annotations. In other words, we're sort of in this unlabeled data setting. The topics in this case are hidden from you. And so then it's not so obvious how to do like this kind of direct estimation. Okay, so that's that's why this is sort of a non-trivial problem. Okay, so let me give you another example now. This is a
T here is the word.
T is one of the topics. There are k different topics, and you might annotate every word with one of these k different things. Sure.
Some prior information about the similarity between words, because if they're all just discrete objects, then there's no way of clustering, because if they're all identical in some sense, indistinguishable from one another. So you start with some similarity notion between words or something like that?
Yeah. So you could imagine a model that has much more prior information that encodes that kind of information. But in this very simple topic model, yeah, there's no such sense.
Every word is in only one topic?
No, not necessarily. Yeah, and so this is one very, very simple model. It makes like a slew of unreasonable assumptions, but still yet somehow it seems to do a reasonable job at capturing thematic topics. Okay, so let me give you another example. This is a very famous story in statistics. Okay, so this is about some data that I think a friend of Carl Pearson went on vacation, and what they do on vacation is they go to the beach and look at crabs, and then they measure various things about these crabs. And one of the things that they measured was this particular ratio of how wide the forehead is to how long the body is, and so this friend of Carl Pearson kind of measured these things and then plotted them, drew a histogram of these things, and it did not look like a normal distribution. So he thought that was very abnormal. Okay, so it looked like this, and it looked kind of skewed to the right. It at least was not even symmetric. And so Carl Pearson said, okay, perhaps it's not just one population of crabs. Perhaps it's two different subspecies that somehow got mixed together. And indeed, he figured out a way, using what's called the method of moments these days, of fitting two different Gaussian distribution to the data and with different proportions. Okay, so this is a very common phenomenon in when you deal with data, is that the data that you have does not really come from just a single population, but multiple populations that get mixed together. And you'd like to learn something about each of these individual populations. Okay. So a Gaussian mixture model is one of such model for this.
Did they actually check that there are really two?
I don't know.
Actually, later it turned out to be one.
What's that?
Later it turned out to be just one species.
Yeah, I think in fact it was not so clear. Like if you just fit, something that's not a normal distribution, you would have been fine as well. But okay, but anyway, regardless of whether that was a good idea back then, people use Gaussian mixture models nowadays for a lot of different tasks. And so one way to think about this as the latent variable model is that there's a hidden variable, h, that takes on k different values with different proportions. And when you generate that, you sort of instantiate the value of this hidden variable, let's say it's equal to t, then the observation you actually make, x, is drawn from a normal distribution with mean mu t and covariance sigma t. And so then the task here is that you want to learn about the means and covariances for each of the individual Gaussian distributions. But you'd like to do this without the colors on the data points. Okay, so once again here, because the data are not annotated by which sort of hidden subpopulation they came from, you don't have a direct way to do estimation. Okay? But that's this is really not a problem. So there's been a century of statistical theory about what can you do in these cases. And it's a very popular approach called maximum likelihood principle. Okay, and following this principle, it says that the estimator that you use, the parameters you should select, are the ones that maximize, that have the highest likelihood given the data. Okay, that maximize this objective function. Okay. And there's a lot of sort of theoretical justification for why this is a good idea. Now, this is an optimization problem. It's nice that you can cast this as an optimization problem. In fact, it's of the form that Elad talked about on Monday. It's just, you just kind of put a negative sign around here, and then you're trying to minimize some kind of sum over your data. Now, the main task is that, okay, when it's the maximization problem, this objective function is not necessarily concave, okay, or the negation is not necessarily convex in the terms of the parameters. But that has not really stopped anyone in machine learning or statistics. We're going to use some kind of optimization algorithm anyway to try to compute this thing. And one of the most famous procedures is called the expectation maximization procedure. Okay, so let me give you an example of this kind of objective function. So the reason it kind of looks like the objective function that we may have seen on Monday. So for Gaussian mixture models, for instance, let's say the data that you have are n data points. These are vectors in, let's say, d-dimensional Euclidean space. Given this data, you're trying to learn or optimize with respect to the parameters of the model. So these are just a set of parameters. And the log likelihood, once you assume that the data are generated IID from the distribution, is just the sum over your data points of this sort of cost function, or I guess this is a negative cost function. And so it's a log of some various parameters and then involving each of the different data points. Okay. So it's not too important what the actual formula here is, but just that it sort of fits the kind of format that we've seen in terms of using optimization for machine learning. Okay, so this is actually a very sensible thing to do as long as you kind of avoid some degeneracies, like you don't want the covariance matrices to get really small or become singular. But once you set up some constraints, it's actually a very sensible thing to do, except for the fact that this is not going to be easy to do computationally. Okay, so it's very similar to this Euclidean k-means problem, which has been well studied in computer science, and we know now that it's NP hard, even to approximate. Okay, so we can set up these optimization problems to define estimates for our parameters, but ultimately, when you write down the problem, it becomes something that we might say is intractable to solve. Now, of course, there are many reasons why people sort of solve this kind of problem all the time, and sort of they're not sort of fazed by the NP hardness of these problems. And the reason is because perhaps the data that you get, the particular instance of the problem, is not the worst case instance. So it sort of makes sense to try to think about the problem from the perspective of not worst case analysis, but perhaps an average case analysis or a best case analysis. And so that's what we're going to do in this talk. Okay, so we're going to look at the kind of setting where the data are sort of the best possible kind of data you could expect, right? Which is data that actually came from one of the distributions in your model. You're trying to learn, the parameters of a Gaussian mixture model, and you sort of only want to sort of deal with the instances where the data actually were generated from a distribution from that model. So you would hope that at least the algorithms that you develop should work in this case. Okay, so let's make this assumption that the data really are generated from some distribution in the model, and you're just trying to learn the parameters of that unknown distribution. You'd like to produce some estimate of the parameters, such that if you get more and more data, your estimate of the parameters gets closer and closer to the true unknown parameters. Okay, so this is what we call consistency. Okay, so this is something that you can do, and perhaps actually these local search procedures work in this case. And for some kind of very special models, for some fairly simple models, indeed the local search procedure will work. Okay, it will actually be consistent. But the minute you sort of just increase the complexity of these models, these local search procedures start running into problems. They, depending on where you initialize, they could get trapped in these local maxima that are actually very far from the global maximum. So okay, so what do practitioners do? They will, this is local search, so you have to initialize the local search somewhere. They'll just initialize it from many random points. And okay, if you initialize it close enough to the unknown parameters, it turns out it will work. It will sort of give you a reasonable estimate. But of course, it might take a long time for you to initialize sort of at the right answer. So this is why, the other kind of issue is that we don't just care about what happens when n goes to infinity. We'd like to do all of this with a reasonable sample size. So ultimately, we also care about, providing correct answers or approximately correct answers with high probability and with a reasonable sample size and running time. So even in this kind of best case scenario where the data really are generated from a distribution, from a distribution in our models, we still would like to provide some kinds of pack-style guarantees. And in this case, it still can be hard to do, okay, under various kinds of assumptions. Okay, even in the case, it's kind of realizable setting, it's not so clear how, for some of these learning problems, whether we can do it. And this is sort of various kinds of cryptographic barriers or computational barriers where you encode some kind of average case hard problem to just look like a learning problem in this case. Or there are, some information theoretic barriers that say that, there are some distributions that have very different parameters but look very similar, but have, are very similar in total variation distance. In these kinds of cases, it seems like you might need exponential running time or exponential size, exponential number of data.
If the distributions look similar in total variance, why do you care about estimating the parameters? Why isn't it a good answer to give another distribution that is almost identical?
Yeah. So that's a very fair question. So if the distributions are actually very similar anyway, maybe you're not going to look at the parameters at all. But if you remember back in the the original problem, we wanted to learn something specific about the two different populations, and if they could have very different means, and you would like to know what those different means are. If you really did want to learn something about the parameters to describe, rather than just the distribution.
Yeah, but, it's an artificial model to start with. It's not, you're not discovering real truth. So.
No, I mean, the means really are something that you could be interested in learning.
Well, if the variation distance was like really small, then I feel like there ought to be bounds on like anything significant that you could observe about the model ought to be. I feel like that ought to be bounded too. That's I guess that's the feeling.
I mean, in some sense, I feel like this is just that you have the wrong metric on your parameter distance. I mean, if you got a Gaussian with standard deviation 10 to the 10 to the 10, you're not going to be able to accurately determine the mean even with a bajillion samples.
Yeah. So I mean, so these kinds of hardness do not have that kind of issue, though.
I mean, they have exactly that kind of issue.
I mean, so the variance of these Gaussians are not that small in these cases. Right. So the parameters are sort of far apart from each other, but the distributions.
Well, what I'm saying is that this is entirely a function of having the wrong metric on your space of parameters.
Yeah. Okay. That's probably fair. Yeah.
Or it shows there's a lack of robustness within the parameters you uncover.
Yeah, so these are fair points. That in some of these cases you don't really care about, these various kinds of distinctions in the parameters. But I think in these cases they are actually quite far from each other. Even like in L2, but maybe if L2 is not the right metric, then yes, you should probably do something else. Okay, so regardless of whether so yes, there's sometimes the information theoretic hardness is not perhaps can be subverted by just kind of looking at a different objective. But with these kinds of objectives that we care about, there still are ways to get around the barriers, and there's been a number of things proposed in the literature. One of them is to make some kind of assumption that sort of rule out some of the hard cases. So you rule out the case, let's say in the Gaussian mixture case, where the different Gaussian distributions are extremely close together. If you just rule that out from the get-go, it turns out there are a number of efficient algorithms that can do the learning. Another kind of assumption that you could, sorry, go ahead.
Are you assuming the covariance is diagonal here?
Yeah, so didn't even define what this is, but this could be maybe the spectral norm of the covariance matrices. So besides these kinds of separation conditions, you could rule them out based on some kind of structural properties of the parameters. For instance, you might assume various parameters are sparse, have a lot of zeros in them, or you might assume kind of very special patterns of zeros in the parameters. And these things have also led to efficient algorithms. So in this talk, we're mostly going to be talking about conditions that are, in some sense, typical or generic. So for instance, like let's say that the means of the Gaussians are in some general position or linearly independent. Okay. And so making these kinds of assumptions, it turns out there's a very broad class of techniques based on something called the method of moments that will work in these cases. So that's what I'm going to talk about in this tutorial. At a very high level with the method of moments, the basic idea is that you first determine some function of the parameters that you want to estimate that you can actually estimate from just the observable data, okay, just from the non-hidden data. So some function of the data that you can actually observe, you sort of determine how this thing depends on the parameters that you're trying to estimate. Okay, so this is something that depends on the distribution and the parameters. Then what you do is using the data that you actually have, that you observe, you can form some estimate of that quantity, of these moments. And once you've estimated these things, you can just set these things equal to each other and solve the equations. Okay? You should solve the equations for theta in this case. Now, of course, you have to ask, first of all, which moments should we look at, and how do we actually solve these equations? And so in this talk, we'll look at, it turns out for a lot of the models that we want to consider, fairly low order, perhaps third order moments will suffice. And the way we solve them, it will be to write these things down as some kind of approximate tensor decomposition problem. And there are efficient algorithms for finding these decompositions.
So I'm not sure I understand the last equation. Is it the empirical estimate of eta, or is it empirical?
Yeah, so this is just an empirical estimate of this quantity.
So there should be a subscript eta there on the right-hand side?
Yeah, so this is some expectation with respect to the distribution with parameters theta, the unknown parameters theta. And you estimate that this is something you can observe just from the data.
Yeah, but the empirical on the right-hand side at the bottom should also have a theta?
Yeah, so this is based on data generated, let's say, from the distribution with parameters theta. So it's just your estimate of it. This is maybe like an empirical expectation. So it's just a bunch of numbers that you actually compute based on your data. And you solve this equation for theta.
I see. You want to find the theta that will match it.
Exactly.
Kind of related to that question. So a maximum likelihood, if in the misspecified case, would converge to like the distribution just closest to the data generating distribution in the KL sense. Is it obvious what it's going to do in the misspecified case?
Unclear. So I'll mention that in like the next slide or so. Okay. I didn't mention step 4, but step 4 is usually something that's done in practice, and also you can analyze in theory. Usually, what you'll do is once you come up with estimates based on method of moments, you will sort of fine-tune them, perhaps using EM or some other local optimization based on the likelihood. Okay, so that's at a very high level what the method of moments looks like. Okay, so as Ambush has already alluded to, there are a lot of issues with this technique. For instance, there's some nice properties of maximum likelihood where you can interpret, what the solution gives. You can have some interpretation of the solution, even if the data was not generated from a distribution from your model. That's called model misspecification. So it's not so clear what the method of moment does in those cases. There's some kind of interpretation because some of the algorithms we develop are based on optimization, and they will say that you're trying to optimize, find parameters that at least match or approximately match some of the moments. But that's not as compelling as, say, finding a distribution that has low KL divergence to the empirical distribution. So that's increasing handling model misspecification or increasing robustness is the important issue. We currently don't have a very general methodology for coming up with these estimators, sort of guided by examples and some sort of ideas that we've seen in the past. It's also not so clear how to incorporate prior knowledge, at least in a very general way. And it'd be also nice to be able to incorporate user feedback, perhaps in some interactive kind of setting. And so these are some issues that I think would be great to work on. Okay, so let me just give you an outline for the next half hour and then the hour after the break. We're going to look at a very simple model first, and to illustrate this technique. It's a topic model for very simple kinds of documents that just are about one topic. We'll talk about some issues in terms of identifiability and give a very simple procedure for doing the parameter recovery. Okay, assuming that, let's say, you can perfectly estimate these moments. Then I'll talk about some extensions of this to other kinds of models that are perhaps a little bit more interesting, various kinds of mixture models, and models that have what I'll call multi-view structure. And at the end, we'll talk about some more error-tolerant algorithm that you would actually consider actually using in practice. Okay, and I'm not going to talk about like a whole slew of other work that people have done using this kind of basic idea or similar ideas. For instance, a lot of these ideas are also used in doing independent components analysis, learning much more interesting topic models like latent Dirichlet allocation, doing some kinds of community detection, learning grammars, various kinds of noisy or Bayesian networks, some non-parametric Bayesian methods, various kinds of models that are used in applications, and some kind of interactive learning settings where these kinds of latent variable models come up. So there's a lot of, people have found a lot of uses for this general methodology, but hopefully I'll just give you a flavor of how some of these things look from the few examples I mentioned already. Okay, so let me start now with the warm-up. The topic model for single topic documents. Okay, so remember the topic model that we described in the introduction. We have k different topics. So topics are just distributions on words. And each document could be about multiple topics, but I'm going to make it simpler and just say there's only one topic for each document. And we're going to pick a topic, T, with probability W sub T. And the topic is not available to us, okay? So it's hidden from us. And we just observe the words in the document, and the words in this model are drawn IID from the topic distribution, so the distribution on words for topic T. Okay. And so remember, the problem is that you're given a collection of documents. Let's say they're of length L, an IID sample of documents according to one distribution from this model. And your goal is to estimate the parameters of that distribution. Okay, so kind of a related question is, I sort of already introduced this other hyperparameter L. It's sort of the length of the document that you observe. Let's just say they're all the same. So basic question is, how long do the documents actually have to be?
So do you pick a different T for each document? Is that right?
Yeah, so each document, the way a document is generated, you pick the topic according to the way it's W1 through WK.
You know the distributions a priori?
No. So these are the things you're actually trying to learn, the W's and the PTs.
Oh, and both, okay.
I guess you could we could simplify it even further and just say maybe it's uniform at random. But okay. Okay. So remember. Okay. So again, this is the generative process that we have. And so if you just have documents that are just a single word, okay, this is maybe like a very extreme form of Twitter, okay? So just have a random tweet and it's just a single word. Can you ever hope to learn these parameters from such observations? No, so try saying no. So why is this the case?
Because there's no structure. I mean, the only structure is imposed by co-occurrence of words in the same document. And if there's no co-occurrence, then there is no structure to be found.
Okay. So what Shai said, okay? So you're not going to be able to identify any of the parameters from these kinds of documents, right? Because, you know, there's any distribution that you could learn, you're just going to be learning something about the marginals on the words, and that could arise from any number of mixture distributions. Okay, fine. Okay, fine. Okay, what about two words? Okay, this is not so extreme Twitter. Okay, so in this case, let's think of this thing as a probability vector. Then the distribution on pairs of words. Now, let's ignore the issue about order. It's just PT transpose, right? So the rank 1 matrix, the probability matrix, these entries all sum up to 1. And a random document will be drawn from this mixture distribution, right? So a mixture of these distributions on word pairs.
So it becomes something like bi-clustering.
Bi-clustering, okay. Okay, so Chai says yes. Does everyone else say yes? Can you do it from?
Have the same weights, then you can't do the. I mean, if you have the same weights, then you can't really isolate the two top weights.
Yeah, so the weights, okay, so here it is important that the weights are some of the parameters here. So if you don't know the weights as well. Okay, so the answer turns out to be no. And so here's one example where these two different distributions, this one without the twiddle, these with the twiddles, actually give rise to the same distribution on word pairs, but the parameters are actually fairly far apart. Okay. Okay. So fine. So the answer turns out to be no in this case.
Just the notation on the top.
Yeah, sure. So P1 is a distribution on words. In this particular case, there are only 2 words in your language, and it occurs with this topic occurs with probability half, and this is the same for the other topic. And then this is a different distribution with 2 topics, again on vocabulary of length size 2, slightly different parameters, but they generate the same distribution on word pairs. And
Essentially, you're saying that the matrix decomposition is not unique. So that's
yeah, exactly. So it's just because you ultimately get some matrix, some matrix, probability matrix, and it has different decompositions into parameters for this model, and you can't tell which of the correct decomposition is the right one. Okay, so that's absolutely right.
Is K hidden?
K, you know, I tell you is 2. I tell you K is 2 in this case. Even so, it's still a problem. Okay, so you can identify parameters from like 2 documents. Okay, so, and you could have also concluded this from like a heuristic based on parameter counting. There are sort of too many parameters to try to identify from the number equations that you write down when you just use 2 word documents. Okay, but once you go to 3, finally it is actually identifiable. Okay, so now we're going to look at the distributions on word triples. Okay, so distributions of triples of words. Okay, and so for one of the topics, it turns out to be a rank 1 tensor. Okay, and a random document will be drawn from the distribution that's a mixture of these rank 1 tensors. Okay, these probability tensors. Okay, and so the claim is that in this case, yes, you can identify the parameters as long as these the parameter vectors are linearly independent, and of course the weights should be positive. And also the parameter counting heuristic, where you just count the number of parameters, count the number of equations. It's kind of clear that it should be the case here too. You should be able to sort of solve for the parameters. Okay, and so what's sort of nice is that this claim is implied by a much more general result on tensor decompositions and the uniqueness of these kinds of decompositions into a very simple form. And there's actually an algorithm for finding these decompositions due to Jennrich. Okay. So before I tell you about Jennrich's algorithm, let me just give you a very, very high-level overview about tensors, just because they're a little bit different from matrices. So matrices are a special kind of tensor, so they're just tensors of order 2. But I think sort of the simpler way to think about matrices and the concept of tensors is to think of them as the bilinear functions or bilinear forms that map pairs of vectors to real numbers in this case. So here's the formula for that function. Okay, so you have M on XY, it's just X transpose MY, where M is the usual tabular form of the matrix, and you can write out explicitly what the function value is. And the way you describe a matrix, of course, is just, let's say, by d squared numbers, or just the d squared different function values that it can take on as you range over sort of, let's say, basis elements. Okay, so then tensors are just the same thing, but a higher order generalization of this thing. Okay, so let's think of, we're just going to usually use third order tensors, but of course it generalizes. You can describe the tensor by, let's say, in this case, as a d to the p different values, just the values that the tensor takes, this function takes on as you range over the different combinations of basis elements. You can also think of it as like a cube or a hypercube of numbers. This sort of analogous formula for the function value. And there's the concept of a rank 1 tensor. So this is going to be important for our notion of a decomposition. A rank 1 tensor is just the sort of atomic tensor that you get by looking at this kind of tensor power of different vectors. The value that this particular tensor takes on when you evaluate it at these different arguments is just the various kinds of, you just pair up the inner products of the different sort of modes of the tensor and then multiply them together. We're mostly going to look at the symmetric case where it's just the same tensor, tensor product with itself. I'll use this notation with the kind of tensor exponent. Okay, so of course I always have to give this caveat about when you're dealing with tensors, is that most of the problems that you would like to solve regarding tensors that you think were easy for matrices, they turn out to be hard for tensors. I'm not going to say any more about this, except that it's maybe perhaps interesting or remarkable that we can do anything at all, and that this algorithm that I'll describe to you actually exists and is computationally efficient.
So that's like, when you say it's going to be hard, does that like include like the I guess the order of the tensors? So like if I said, oh, I just want to do this for tensors of order 3 instead of letting the order grow higher, would they still NP hard?
Yeah, even yeah. Okay, so somehow 2 is a special case. In this case. Okay, but this algorithm actually has generalizations to higher order tensors, but I'll just describe it for the third order tensor. Okay, so this algorithm, we're sort of given a tensor that has a particular decomposition, one that looks like this, the sum of these rank 1 tensors. And we'll assume that these rank 1 tensors arise from vectors that are linearly independent. Okay, so it's kind of a promise problem that you're given a tensor that has this kind of decomposition, and then your goal is just to find the decomposition, find these k different vectors. Okay, and just to make it even easier, let's just ignore the issue about the scaling. We can find just the directions of these various vectors. Okay, so Jennrich's algorithm is based on a concept called collapsing a tensor from, in this case, a third order tensor down to a matrix. And the way it works is that you think of a tensor, remember I said it was in this case, a trilinear form. You think of it as a linear map from vectors to matrices. And it's just what you would get if you apply it to a vector. The matrix whose jkth entry, it's just the evaluation of t on x, same x there, and let's say the jth and kth coordinate basis vectors. It's kind of like currying in functional programming, if you like functional programming, sort of in a sense. Okay, so that's Jennrich. That's sort of the basic tool in Jennrich's algorithm. The way it works is that you're going to collapse the tensor in 2 different ways. You'll do this using 2 different, let's say, random unit vectors drawn uniformly at random, x and y. You collapse the tensors in 2 different ways with x and y, and then you compute this matrix product. Okay, so the t of x is the matrix, t of y is the matrix. You multiply t of x and a pseudo-inverse of t of y. This is another matrix, and what Jennrich's algorithm will do is then just return the eigenvectors of that matrix. Return the eigenvectors corresponding to non-zero eigenvalues. Okay, so it's a very simple algorithm, and the analysis is also fairly simple. So let me just go through the analysis. Okay, so it's based on collapsing the tensor into matrices, and since collapsing is sort of a linear mapping, the collapsing of this tensor with this particular form is just the collapsing of each of these terms.
So we are assuming k is less than or equal to d here, right?
Sorry?
We are assuming k is less than or equal to d here.
Yeah, because these vectors are linearly independent. Yes.
Okay, that's the assumption.
Okay, so the linearity here is just when you collapse the tensor t with vector x, it's just collapsing each of these tensors with vector x, and then you add it up. In that case, it's just the inner product of vt and x times vt transpose. Okay, so it's the rank 1 matrix scaled by this particular inner product, and then you add up these rank 1 matrices. Okay, I'll write it in the more familiar matrix notation, where this matrix V is just the matrix of all of the vectors, v1 through vk, and d sub x is a diagonal matrix whose entries are these inner products. Okay, and so then this collapsing of the tensor is just v times dx times vt transpose. So we do this with vector x. We also do this with the vector y. And based on these assumptions that we made about the tensor and the way we've chosen the vectors x and y, a number of consequences follow. Okay, so first of all, this matrix has rank k because we're assuming that the vectors are linearly independent. Secondly, these two diagonal matrices, dx and dy, are going to be invertible with probability 1. Okay, we chose these vectors uniformly at random from the unit sphere. These inner products are not going to be 0. None of these inner products will be 0. So both of these matrices are invertible. In particular, we can invert dy, and then if you look at dx times the inverse of dy, this is a little bit not as obvious, but it's also true that the diagonal entries of this matrix will all be distinct, because the chance that any two of them are the same is a measure of 0, has probability 0. And then finally, the matrix that Jennrich's algorithm actually computes, tx times pseudo inverse of ty, will have this form, v times some diagonal matrix times pseudo inverse of v. And then you kind of look at this and you realize that this is diagonalizable. Okay, the eigenvectors, in fact, are just the columns of v, which are v1 through vk.
So can we think about it as if we're doing random projections of the tensor?
Yeah, it's basically sort of random. If you think of the tensor as a cube, you're sort of randomly combining the different slices of it. Okay, so this is why Jennrich's algorithm just computes the eigenvectors of that particular matrix that correspond to non-zero eigenvalues, because those things will be up to scaling just the vectors v1 through vk.
So here this analysis uses the assumption that they are linearly independent, but it looks like the assumption is used sort of quantitatively, right? So things hold almost surely. So can you say something almost linearly independent, for instance? This algorithm will work with some probability?
Yeah, so what you really need if you want this to work when perhaps there are errors and you have finite precision, is that you want it to be very linearly independent. So not just, okay, if it's not linearly independent, you're sort of in trouble, but if it's just barely linearly independent, you could also be in trouble. So you really want them to be sort of well-conditioned.
Barely linearly independent means that you can compose something that is close to 0.
Yeah. So for instance, this matrix has very like the case singular value of this matrix is very, very small. You're also sort of numerically in trouble. Okay, but let's kind of ignore this issue for now. We'll get back to it in the last part of the talks. Yeah.
Where are we really using that the 3 VTs are the same in this proof? Because if
we can generalize this to sort of the asymmetric case as well. This is just a very simple form of Jennrich's algorithm. You can generalize it to asymmetric case, and in fact, you don't need all of these vectors to be linearly independent. Okay, so that's it. That's the algorithm. And to see how it actually applies in our, when we go back to our topic model, remember our topic model, we had this tensor of word triple probabilities, and it had this particular form. Okay, and we can kind of make it look like this if we identify the VTs with, let's say, the cube root of the W times PT. And then the condition that we had, that I set up in the claim, was that, that these distribution probability vectors are linearly independent and all the weights are positive. So when that happens, then these vectors are also linearly independent. So the Jennrich algorithm applies in this case. So what does that mean? That means we can look at this tensor, apply Jennrich's algorithm to it. We'll get some eigenvectors that are actually in the same directions of these components. Kind of easy to then sort of do some normalization or something to get the actual distributions on words. And then from there, it's also not too hard to get the various, the mixing weights. So that's the identifiability proof. So once you have the distribution on these word triples from the model, you can actually extract out all of the parameters. Okay, so just to recap, so for this very simple latent variable model, this kind of very simple topic model, it's just a mixture of multinomial distributions. The parameters are actually identifiable, as long as the parameters satisfy these linear independence conditions. They're identifiable, can be recovered just from the distribution on 3 Word documents. Okay, and it turns out that if you just had a distribution on 2 Word documents, unfortunately, without some further conditions, it was not identifiable. Okay, but 3 words, doesn't seem that much more onerous to, distributions on 3 words, not that much worse to estimate than distributions on 2 words. As you get, higher and higher, maybe it gets much more difficult.
So
sorry.
you gave
Go.
a counterexample for 2 words. You had to kind of make a particular example. What if you picked it randomly, just like what you're doing with the 3 word thing?
Yeah.
But for 2 words, you will need orthogonality, otherwise it won't be even if it is linearly independent.
Yeah, I think you can construct
Is not enough.
other examples as well, but
I'm sure there's an example for 3 word as well, right? Or not?
yeah, but for 3 words, yeah, I think for 2 words, it's actually even just the number of parameters you want to estimate. You could have like a whole subspace of solutions.
So this is under the assumption that for every triple of words, the probability.
Yes.
Now we want to do sampling because we don't know those probabilities, right? So there's the expression of sample complexity.
Yeah. So what Shai is saying is that we don't actually know the true probabilities. We actually have to estimate those things from data. But at the very least, these are things that we can estimate from data because these are probabilities of events that we can actually observe. Okay? Whereas we don't actually observe the topics, so we can't directly estimate, for instance, these various these distribution for each of the topics. But we can directly estimate the distributions of word triples from the.
Many word triplets.
Yes, that's true. Yeah.
How about the uniqueness of this decomposition? Like the example you gave about 2 word example where you had multiple possible decompositions of a rank 2 matrix. Don't you have the same problem here that when you do the eigen decomposition, you get some decomposition for this tensor, but it may not be same as what you want?
Yeah, but this claim is saying that that's actually not possible. As long as the claim was that as long as these probability vectors are linearly independent, there's no other way, and these W's are positive, there's no other way to get the same distribution on word triples. And sort of proof by construction is that this algorithm will actually, given this distribution on word triples, it will give you just exactly one set of parameters. The only one that will arise that way. Okay, so that's the warm up. Okay, just to, I don't know if this is important, but just to show you that this thing, actually, even though this is such a simple model, it makes like a million unrealistic assumptions, it actually does something semi-reasonable on some real data, even though, it's not sort of the most sophisticated kind of latent variable model. So we actually applied this thing into some articles from New York Times from like early 2000s or so, with reasonable sized model. We had a vocabulary size of nearly around 100,000 words. Tried to learn the model with 50 different topics. And in terms of predictive performance on held out documents, I know this is unclear whether this is a reasonable measure. It seemed to do very well compared to some of the existing methods for learning topic models, even more sophisticated topic models. If you just use Gibbs sampling with latent Dirichlet allocation, the training time can be quite long because you have to expect this Markov chain to eventually mix. There are some better kinds of Markov chains that you could use, some better kinds of Gibbs samplers to use, and they converge much more quickly and give you much more reasonable estimates. And so our algorithm, based on the method of moments, does comparably in this case.
So, Daniel, is there any way to look at not the training, but
like sample complexity or something? Yeah, we didn't actually do that experiment. But,
because for the training, the loss goes, look at any reasonable model, the loss should go down, right? Even for the training.
with training, more training, you get better results.
No, shouldn't.
It's not clear.
Does the algorithms recover the global optimal or local optimal?
So there's not, an obvious objective that we're thinking about here. So doesn't really make sense to talk about a local or global optimum. In terms of this held out performance, we don't know. We couldn't check whether we were at the local or global optimum.
So when you do the training, you actually did the diagonalization of the matrix and computed aggregate, or should we do something else?
Yeah. So Misha's asking if I actually used that diagonalization procedure. No, we used something slightly different. I'll get to that in a bit. Okay, so this are some of the topics that this model learned, or this algorithm learns. So these are the various, some of the 50 different distributions on words. I've given them some names. These, of course, don't come from the algorithm. And the words that I'm showing are the most probable words, the 10 most probable words under each of the distributions. And they seem to be fairly coherent. So there's some topic that places large probabilities on sort of economic-related words, on baseball-related words, and so on. This one kind of tells you that it's from like the early 2000s, a bunch of election-related words, and so on.
The model generated the topics, or you gave the topics?
The names, yeah, I made these up. Yeah.
Is it like possible to, so we're doing estimation here, like what about like uncertainty estimates, like confidence intervals, like if I get a non-zero probability, how, like?
Yeah, so there's not sort of a very nice way to get confidence intervals here. You could get confidence intervals on the estimates of your word triple distributions and then somehow propagate those things through, but I don't think it would be very pretty. So it would be probably the thing that you would do in practice is to use like a bootstrap. Yeah. Okay. All right, so before we go for the break, let me just remind you, so we're trying to develop these learning algorithms based on this method of moments. In this particular case, the procedure was to estimate the distributions on 3-word documents. There are a number of ways you could do that. Counting is one way, but perhaps there are better ways to do it. This is what we call the empirical moment tensor. So it's just some estimate of some tensor that has the nice structure we want. And then we approximately decompose it, perhaps using Jennrich's algorithm, perhaps using another algorithm, and that's how we get the parameter estimates. Of course, there are a number of issues here that have already been brought up. It's not so clear how accurate the moment estimates are. Okay. The procedure that I described to you, this Jennrich's algorithm, may have some issues with robustness. Computing eigenvalues sort of depends on, computing eigenvectors depends on something about the eigenvalues. It's not so clear this is the best way to do that. And this is an extremely simple model. It would be nice if this thing kind of generalized to a little bit more interesting models. So I'll talk about some of these issues. I won't say too much about how do we estimate the moments or these kinds of distributions, except just to say that somehow lower order moments are probably easier to estimate with less data than higher order moments. That's because they will have lower variance. In terms of robustness, I'll describe sort of in the third part of the talk a different algorithm that seems to be more robust and is still computationally efficient. And in generality, I'll talk about in the next part, where I'll look at some other models, kinds of classical models, classical kinds of mixture models, Gaussian mixtures and mixtures of linear regressions, and then models that have a particular structure that I call multi-view structure. Okay, so that'll be after the break.